a finite amount of steps. Actually, the number of vertices is equal to m choose n, where n is the number of vertices, m is the m choose m, where n is the number of vertices, m is the number of linear constraints. And we know that this is the optimal solution because we know that the intersection of many linear constraints creates a convex set. In convex set, if we choose any 2 points, in convex set, if we choose any 2 points, we know that we can draw a line between those points, and this line belongs to this set. So if we are in one vertex, we can draw a line to any of the vertices. So it is not possible that there exists a vertex to which we cannot move from this vertex, and it has a better optimal solution. So any adjacent vertex. So if we start, for example, in this vertex, and if we move to this one, this is the optimal solution. If we select some intermediate vertex, we know that this vector to the optimal solution can be constructed from these 2 vectors. So that's why we know that we can always improve we can reach the optimum by moving to the by choosing vertices which are improving the solution. So this is what I mentioned. We showed that the optimum is located in one of the vertices. It is possible that it is located in 2 vertices. It means that it's located on the line connecting those 2 vertices. So it's located on the edge of the polytope, and the simplex method operates on the canonical form. So this is the form where we have equality constraints, but we can convert the problem to the canonical form. So we can convert the inequality constraints to the equality constraints, as it was shown during the second class, probably. So the things which remains to define is how to find the starting solutions to the initial vertex, and how to choose and move to the adjacent vertices. So just to recall, this is the canonical form of linear programming. So we have a minimization problem, and we have equality constraints. And also the number of equality constraints, so the rank of the matrix A is lower or equal than the number of dimensions, the number of variables which we try to optimize. Otherwise, if the number of equality constraints is greater, we probably have empty feasible set, so we cannot find any optimal solution because there is non-solution to such problem. So in a standard form, the number of variables, number of dimensions is called a dimension. M is the number of equality constraint, it's called a rank, and any x that satisfy those equality equations is called a feasible solution. And if we suppose that the rank of the A matrix is M, so this is our rank of the problem, and we choose M columns from A. Normally we have n columns because we have the dimensionality of the problem is n, but if we choose m columns, which are linearly independent, so it means that any 2 vector linearly independent means that one vector cannot be expressed as another one multiplied by a certain constant, so they are not parallel. we choose such m columns that they are forming non-singular matrix. So non-singular matrix is a matrix for which a determinant is different than 0. And we call such a matrix a basic matrix. So in this example, we have such a system of equations. And if we select, for example, variable x2 and variable x4, they are forming a basic matrix with such a form. So this coefficients from x2 goes to the first column of our basic matrix, and this coefficients from x4 goes to the second column of a basic matrix. But in this case, we also have 5 other basic matrices. We can select any 2 columns, any 2 variables, and create such a matrix for which the determinant is different than 0. And by extracting the basic matrix, we divide all variables in our problem into 2 sets. The first one is the set of basic variables, and the second one is the set of non-basic, or otherwise called free variables. So basic variables corresponds to the columns from which we create a basic matrix, and free variables corresponds to the correspond to the remaining columns, which are not included in the basic matrix. So going back to our example, if we create such a basic matrix, so we are creating it from the second column and from the fourth column, we have the following basic variables. It is x2 and x4, because we choose those 2 columns to create a basic matrix. And the free variables are x1 and x3. So 2 remaining columns creates a set of free variables, and we can express this system of equations using our basic matrix. So normally we have such a system of equations: ax equals to b. So this is our coefficient matrix, and which forms equality constraints, and we can divide it to basic and non-basic variables. So basic variables we have to multiply by the basic matrix. So in this part of equation, we obtain those 2 columns for 2x. So in this part of equation, we obtain those 2 columns. And we have some other matrix B prime. For now, it's not important how it looks like, but it's obviously formed by from the coefficients for free variables. And if we add this part of equation, we obtain the right-hand side of the equation, right? So if we express our equality constraints by this equation, if we multiply them by from the left side by the inversion of our basic matrix, so we take this equation and multiply it on the left side by inversion of B matrix. This becomes 0. It is identity matrix. So we can express it in such a form. Here we have our set of basic variables, and we have some other matrix, which is multiplication for the inverse matrix to the basic matrix, and the matrix formed from the remaining coefficients in for free variables. And here we have the inverted matrix multiplied by the free coefficients. Then we call such a form the canonical or equality form. So if we choose first I variables as the basic one, the canonical form looks like this. So in this side we have a matrix composed of one for each basic variable. So here we have x2, x3 up to xi. And then we have this remaining part. These are the coefficients in this multiplication. And right-hand side of the equation, this b is different. This b is different than this one because it's multiplied by the inversion of the basic matrix. So we call such a system of equation a canonical form. So in our example, if we choose x2 and x4 as the basic variables, then the system of equation canonical form looks like this. So here we have our basic variables, and here we have some other coefficients by the multiplication of these matrices, and some right-hand side of the equations which we have to evaluate. So another thing which we should note is the fact when the three variables are equal to 0 in this system of equation, then such a system has exactly one solution. And this is this solution, right? So if we express this as xb plus version of B matrix multiplied by B prime by three variables. This is equal to inversion of basic matrix multiplied by right-hand side of the equation. If the three variables are equal to 0, then such a system of equations has exactly one solution, and this is the solution where the basic variables are equal to right-hand side multiplied by the inversion of the basic matrix. So such a vector where we have a basic variables and zeros for three variables is a valid solution. So it's a feasible solution to the system of equations. And such solution we call a basic solution because it's composed from basic variables. And if x is a feasible point in our optimization problem, because we have also the range constraints, which most of the time indicates that each variable has to be greater or equal than 0. So if all the basic variables, values for all the basic variables from this equation are greater or equal than 0, then such a solution is called a feasible basic solution. And if there exists such a variable in basic variables which is equal to 0, then such a solution is called the generated basic solution. But we will not consider such type of solutions. In such a case, there's a little difference how the starting vertex is selected. And we also not consider a case where we do not have a feasible solution from solving the equation, but there are some methods which we can apply to modify the equations to find a feasible solution. So if the basic solution is the feasible solution, this is the case which we will consider. So we find a basic solution for the system of equations, and if such a solution is a feasible one, such a solution is the vertex of the polyhedron, which forms the feasible set. So the number of basic feasible solution is m choose n. So we are choosing m inequalities from n variables, and this is our upper bound for the number of vertices which need to be checked. However, the simplex method moves between a feasible basic solutions in such a way that it minimizes this number, because in each move it improves the found solution. So the other question which we need to answer is how to find these basic solutions. So how if we are located in one basic solution, feasible basic solution, how to move to another feasible basic solution, which is the adjacent one, in such a way that we are improving our objective function. So let me first start by solving a system of equations. Just to recall, this is the Gaussian elimination method, which is used to solve such a system. So let us consider the following system of equations. We have 3 variables and 3 equations. So we know that such a system has one solution. And for simplicity, we'll write it in such a matrix form, in a tabular form. So here we have the number of equation and variables with coefficients for each part of the equation. And we are transforming such equations such that in this column we have a vector 1, 0, 0. So we are trying to eliminate this variable x1 from equation 2 and 3 and only leave it in equation 1. And we'll repeat this for all the columns. So to change this column to 1, 0, 0 vector, first of all, we need to divide equation R1 by 2. So if we divide it by 2, 2x1 becomes x1, 2x2 becomes x2, and x3 becomes 1 second x3. And the right-hand side of the equation, 9 becomes 9 divided by 2. And then we need to subtract such amount of this equation from other ones, such we are eliminating this variable x1 in this equation. So to eliminate this 2 from this equation, we need to subtract equation 1 from equation 2. So our new equation is equal to a subtraction of equation 2 from equation 1. So 2x1 minus 2x1 is 0. So here we have 0. x2 minus 2 minus x2 minus 2x2 is equal to minus 3x2. 2 minus 1 is 1. 6 minus 9 is minus 3. And for the third equation, we need to subtract from third equation, first equation divided by 2, or this fourth equation. So 1 minus 1 is 0, 1 minus minus 1 is minus, minus 1 is minus 2. 2 minus half is 1.5, and 5 minus nine divided by 2 is equal to half. And we obtain a vector 0, 1, 0. And we can check by with this equation such that we have to subtract it by minus 1/3. So x3 divided by minus 1/3 is minus x3 divided by 3. Here goes 1. And then we need to subtract some amount of this fifth equation from fourth and sixth equation, such a way that here we have zeros. So here we have 1, here we have 1, so we need to subtract from this equation. So 1 minus 1 is 0, half minus 1/3 is equal to 5 divided by 6, and so on, right? So we are creating here a vector 0, 1, 0, and repeat the same for the third column. So if we have system of equations written down in such a form, we can easily evaluate what are the values for the variables. So This is called the Gaussian elimination, and we can easily see that the value for x1 is equal to 1, value for x2 is equal to 2, and value for x3 is equal to 3. So we often will be writing such table in a form of simplex tableau. So this simplex table is written in such a way that here we have the variables, x1, which is this column, x2, which is this column, and x3, which is this column. Here we have the equality constraints, and here we have the coefficients corresponding to each variable and right-hand side of the equations. And the operation which we did is called a pivot. So a pivot is an operation where we change the coefficients on the jth column and ith row such that we have ith unit vectors. So we have vector 0, 1, 0. So 1 is for the jth column and ith row, and we achieve this by multiplying the ith row by a constant. So in such a case, if we need to have a unit vector with 1 on each element, we need to divide this row by 2, and then we are adding multiplies of this ith row to other rows in such a way that we are changing these coefficients to 0. So this operation is called a pivot. So this is the result of our system of equations after applying pivot on first column and second row. And to summarize how we solve a system of equation using a Gaussian Jordan method, we are solving such a system of equations by performing a pivot on first column and first row, on second column and second row, and third column and third row. And after performing these 3 pivots, you obtain such a system of equations from which we can easily determine what are the values for corresponding variables. And in this way, we can try to obtain the first feasible basic solution. So as I mentioned, the solution may not be feasible because one of the variables might be lower or equal than 0, but we will not consider such an example during this course. So to find a solution to a system of equations, we have to reduce the system of equations to the canonical form due to the basic variables. So consider the following system of equations, and such a system has infinitely many correct solutions because we have 2 equations and 4 variables. So we can find as many solutions as we want, but there is only one solution for if we select a basic matrix. So here we're selecting a basic matrix from first column and third column. So our basic variables are x1 and x3. So these are our basic variables here. Our 3 variables are x2 and x4, so these are the remaining variables, and there exists only one solution where the 3 variables are equal to 0. And we cannot apply this for selecting first and second column because the matrix, such basic matrix, is singular, so it has a 0 determinant. So we write such a system of equation using a simplex table. Using simplex table. So x1, x3 are our basic variables. These are our 3 variables. So we are just rewriting this system of equations to the table. And then we are performing pivots on our basic variables. So we need to perform a pivot on first column and then pivot on third column. So we are making a pivot on first column, first row. So after we do not need to divide this row by any value because we have one already here, but we need to subtract 2R1 from R2. So 2 minus 2 times 1 is 0, 4 minus 2 times 2 is 0, 1 minus 2 times 1 is minus 1, 3 minus 2 times minus 1 is 5. Here we have minus 2. And then we are performing a pivot on third column, second row, so on our second basic variable. And we obtain such a system of equations. And if our three variables are equal to 0, so if x2 and x4 are equal to 0, so this variable and this variable is equal to 0, such system of equations has exactly one solution. And this solution is such that x1 is equal to 3, x3 is equal to 2, and these three variables, x2 and x4, are equal to 0. And this is our feasible solution because right-hand side of equations are greater or equal than 0. So after expressing this as a basic matrix, our basic matrix is equal to the unity matrix. Our matrix for three variables corresponds to these coefficients in second and fourth column. Our basic variables vector is x1 and x3, and our three variables are x2 and x4. So such system of equations has exactly one solution if the three variables are equal to 0. This is just what I mentioned. And to generalize the process of pivot, so because this is the operation which is performed frequently by the simplex algorithm, we can generalize it and apply it as a general algorithm. So let us represent the system of equation in such a form. And to convert a given column to a unit vector, we are choosing an element APQ. So we are selecting P column and we are selecting P row and Q column, and we assign we divide each element in the P column by the value of this coefficient. It will be more visible in this slide. So this is the generalization of the pivot to unit vector. If we select such an element, so for the main row, for this column, we need to divide this element by the selected element. So n is the considered column, p is our row. So if n is equal to q, because this is our selected element, we need to divide the element by itself, APQ divided by APQ. For the second element, we divided this our APN, so p is equal to 2, n is equal to 2, q is equal to 1. So we are dividing this element by this element. The same goes for the third one, so we are dividing A13 by A11. The same goes for the right-hand side of the equation. And in the second row, for the remaining rows, we are applying such an operation. So we are taking the value mn, so it's our considered row and our considered column, and we subtract the value in the corners of they are forming such. We can imagine that it's some kind of a square. If we want to make a pivot on this value, we selecting this value and subtracting by the multiplication of the value in Q column in the same row and value in and a value in n column in p row, and divided by the value for which we are making a pivot. So we repeat this step for all the variables. So it's easy to remember this method as a rectangle rule. So if we have a select element APQ and want to make a pivot on this element, and we need to apply some subtraction and by multiplication of this row on another element. So for example, we want to evaluate what value should be in element AMN. It corresponds to this value subtracted by the multiplication of the values in the opposite corners of this rectangle, and our value divided by the value for which we are making a pivot. So the new value in this element is equal to this, subtract by this multiplied by this, and divided by this element for which we are making a pivot. And it applies to all the values, because if we select the value in the same row, so it's equal to this value minus this multiplied by this divided by this. So it's equal to yes, so it's equal to this value divided by this. So by changing the base in simplex, we are moving to adjacent vertex, and we are doing this by changing the variables which are included in the base vector. So we are selecting certain root element, APQ, and this element has at least one variable positive in a column, and we are selecting this as an element for which we have the lowest value called simplex condition. So this is the value of right-hand side divided by the value in considered row. So we are selecting a row in that column for which the right-hand side of the equation divided by the coefficient in our column is the lowest. We are making a pivot on such column and such row, and by making this pivot, we are changing the variables in the basic vector. So we have such a system of equations. We can assume that our basic matrix is composed from the coefficients from the first variable and the third variable. So our basic vector is x1 and x3. And if we insert the equations in the simplex table, we can find the first basic point. So to do so, to find such a basic point, we are making a pivot on our basic variables. So first we are making a pivot on first column. So this value is equal to this divided by itself. This value is equal to 2 divided by 3, and so on. For example, this value is equal to 2 minus 1 multiplied by 2 divided by 3. So it's 2 minus 2/3. So it's equal to 1 and 1/3, right? And next we are making a pivot on third column, second row. So we have a system of equation expressed in canonical form. From this, we can obtain a basic feasible solution. So our free variable is equal to 0, x2 is equal to 0, and such system of equation has exactly one solution. So in this solution, x1 is equal to 3, x3 is equal to 3. And then we can write it in shortened form to save some space. So here we are writing basic variables. Here we are writing free variables, and we do not need to write the coefficients for free variables because we know that's equal to unit vector. So it's the same as if we write here x1 x3. Here x1 is 1 and here x3 is 3, right? So this is exactly the same. And to introduce a new variable to the base, we are making a pivot on one of the columns of 3 variables for which we have for row for which we have a positive coefficient. So this coefficient has to be positive, so we can only select this basic variable to move it out from the base and to introduce a free variable x2 into the base. And to do this, we are making a pivot on this variable. So if you would write this in extended form, here we have x1. So the value for x1 is 1 divided by 3 divided by 4, so it's 4/3. Here we have 0. So this value is equal to this value divided by minus this value, because according to this rectangular rule, it's equal to 0 minus 1 multiplied by minus 1/4. So here we have minus 1/4 divided by this. So we have minus minus is a plus. So you have 0 plus 1 divided by 4 multiplied by 3 divided by 4. So it's equal to 1/3. So in other words, it's equal to this divided by this with minus 1. So we introduce this variable into the basic vector. We do the same for the coefficients. For example, the value for this coefficient is equal to 3 multiplied by minus this multiplied by this. So it's plus 3 divided by 4 divided by this. So it's 3 plus 1. That's why here we have 4. And then we have a new basic vector, x2 and x3. We have new free variable, x1. Now we can repeat this step. So we can select such a column for which we have a row with a positive coefficient. So we have 2 rows with a positive coefficient. So we are calculating a simplex condition. So this simplex condition is equal to the right-hand side of the equation divided by the coefficient in the selected column. So 4 divided by 3 is equal to 3. 4 divided by 1/3 is equal to 12. So we are selecting the row with a lower simplex condition. So we are selecting this row. However, this was the row which we already, this will lead to the base which we already had. So from this, it follows that the first base is equal to x1 and x3, and the solution to such a system of equation for which we have a free variables equal to 0 is equal to 3, 0, 3, because here we have 3 for x1, here we have 3 for x3, and for x2 we are assuming it's equal to 0, and our second base is equal to x2, x3, and our solution is equal to 0 for 4. Because free variables equal to 0, and here we have a simple solution for remaining 2 variables in the base. So just to recall, if the linear programming is written in a other form than the canonical form, we have to use various techniques to transform the problem into the canonical form. So just to recall these techniques, assume that we have such 3 types of problems, and we will go one by one and reduce them to the canonical form. So in the first example, the problem is the fact that we have inequality constraints. So we are introducing additional variable x5, which is greater or equal than 0. And by subtracting this variable from this equation, we can replace the inequality constraint by the equality constraint, and all the variables have to be greater or equal than 0, including x5. So here the index should be 1, 2, 3, 4, 5, because this variable x5 also need to be greater or equal than 0. In the second example, we have 3 inequality constraints, so the procedure is the same. We assume that x is equal to x4, we will name it x4, y we will name x5, and we introduce 3 variables, x1, x2, x3. And if we add those variables to these equations, we can replace the inequality constraints with the equality constraints. And this is our third example. In this third example, the problem is that variable x1 is unconstrained. So for variable x2, x3, we have a constraint that they are greater or equal than 0. For x1, we do not have such a constraint. So we can reduce this variable by determining its value from one of the equality constraints. So for example, if we take the first equality constraint, we can express it as x1 is equal to 5 minus 2x2 minus x3. And we can insert this value for x1 into the second equation into our objective function. So after inserting this value for x1 to the second constraint, we are reducing the number of variables. So the general steps to solve the linear problem with simplex method is firstly to convert the model into the canonical form, to the form where we have only the equality constraints, convert the minimization problem to a maximization problem, and reduce the system of equations from the coefficients in equality constraints to the canonical form, and then find the basic solution, which hopefully is a feasible one, and then create a simplex table and introduce basic variables to the solution by making a pivot in such a way that we are improving the solution. So these are the steps. So we have an optimization task. We are reducing it to canonical form, so we need to introduce 2 additional variables to convert inequality constraints to equality, because here we have lower equal, then we are adding additional variable. Here we have greater equal, so we are subtracting the additional variable. All the variables are greater or equal than 0. We convert the problem to the maximization problem, so we are multiplying our original problem by -1. And in such a way, we are changing the minimization problem to the maximization problem. And we can write the objective function as a 0 equation. So if we subtract this f of x, f from x from the right-hand side of the equation, it should be equal to 0. So we are subtracting this from this side, minus f of x. And in such a way, here we have a 0 instead of a maximization, right? So if we write objective function in such a form, it's another equality constraint, so we can insert it into our simplex table. So instead of the naming of variables, here we have the 0 equation. Here are our two equality constraints, coefficients for these constraints. Here we have the objective function and the value for the objective function, which is equal to 0. And this coefficients for the zero equation are called optimality coefficients, or otherwise are called a reduced cost. And they are describing the values for the variables for our objective function. And then we are reducing our system of equations to the canonical form. So we are making a pivot. We are selecting two columns for the basis. And after selecting those two columns, we are making a pivot. So we are making a pivot, for example, on the third row. So these are our first basic variable, and on the first row, first column, third column, and first column. So this is our second basic variable. After making a pivot, we are reducing a system of equations to the canonical form. And then we need to choose another variable which we introduce to the base in such a way that we are improving the solution. And here we have the following assumptions. If at least one reduced cost is positive, so one of the coefficients in this zero equation, if at least one is positive and the coefficient on any variable is positive. So, for example, here we have a column, we have a positive reduced cost, and we have a positive coefficient in the first equality. It is possible to improve the objective function by introducing this variable instead of x3 to the base. If all reduced costs are negative, so we know that we found an optimal solution. If all reduced costs are non-positive, there are infinitely many optimal solutions. And if the column with coefficients, except for the cost, reduced cost. So, for example, if here we have 5 and here we would have -2 and -1, we can increase the value of the objective function as much as you want, so the function is unbounded. And to explain it, let's look what happens to the coefficient a00. So this is the value of the minus value of the objective function. When a variable xi is introduced to the base. So, for example, if this variable is introduced to the base, this value becomes this minus this multiplied by this divided by this. So this is exactly what we have here. So the difference between current value and the new value, it's a difference of minus f function, so it's equal to the new value minus the previous value. And because we are interested how our original function, not a minus function, will change, we need to multiply this by -1. So we know that if we introduce selected APQ variable to the base, we know that the objective function will change by this amount. So A0 Q multiplied by AP0 divided by APQ. Divided by this. So if we introduce this variable, we know that the objective function will increase by 5 multiplied by 2, so it's 10 divided by 2 is equal to 5. So we know that APQ is greater or equal than 0 because we're selecting only an element in a row for which this value is positive. So we cannot select for example, this coefficient, so we cannot introduce S1 instead of X1 because this value is negative. So we are selecting such an element which is positive, and we know that the right-hand side of the equation is also positive. So if the reduced cost is a positive, this equation is also positive, because we are multiplying positive number by the positive number and dividing it by the positive number. So we know that the objective function is increasing, or A0 is decreasing. So our minus f function is decreasing. So if minus f function is decreasing, the f function is increasing, right? Because it's multiplied by -1. So this explains the case number 1. So if at least one reduced cost is positive and the coefficient for some variable is positive, so for example, for this variable is positive, there is a room to improve the objective function. So we have the objective function expressed in such a form. This is our objective function. So we are moving -f on the right-hand side, and A0 we are moving on the left-hand side. So here, that's why we have -A0. We can increase the value of the objective function by decreasing the value of by decreasing the value of S1, assuming that we are not touching other non-base variables. So if we decrease the value of our introduced variable to the base, we also need to decrease the value of A0. So we are increasing the value of -A0. So we are increasing the value of our objective function. Because if we decrease the value for S1, we need to increase the value for the right-hand side of the equation, and other non-base variables are equal to 0, right? So we know that we are increasing the value of the objective function. So in another case, if all reduced costs are lower than 0, so this is this case, we're unable to choose such a variable that will increase the value of the function. So we, for example, select this element, which is a positive element, and the value of the function will change according to this equation. So -5 multiplied by 2 divided by 2, this number is negative. And if all reduced costs are negative, this value will be negative, and we cannot select such a positive element such that the value of the objective function will increase. So for example, this is our objective function, and it's bounded by the assumption that all the variables are greater or equal than 0. So the maximum value for this objective function is equal to -A0, because if any variable is greater or equal than 0, we will decrease the value of the objective function, because each of the variables is multiplied by the negative value. So the maximum value of this objective function is equal to -A0. And in the third case, when A0 is equal to 0, so if one of these reduced costs is equal to 0, we can introduce the variable into the base, but we will not improve the cost function. So it doesn't, if we change the value for some variable which is multiplied by 0, it will not affect the value of the objective function. So we are selecting another point which is lying on the segment on the edge between two base variables which have the optimal value. And in the third case, if the positive cost is if the reduced cost is positive, and if all the coefficients in that column are negative, we are able to increase our objective function infinitely. So, for example, this is our equation, and we can increase the value of the objective function by increasing the variable x4. So if we increase the x4 if we increase the x4, we need to increase the a0. If we increase the x4, we need to increase the a0. No, if we decrease the x4, if we decrease this value,
Sorry, Professor, but we cannot hear you.
yeah, I know. I'm thinking about this sentence because I got a little bit confused. Okay, if this variable is positive, we can increase it as much as we want. All right. If this variable is positive and if all the coefficients are negative, we can increase this variable as much as we want. And if we increase this variable, we are also increasing the objective function. And we can do this because we are always satisfying the equality constraints, because if we increase these variables, these coefficients are negative, so we are decreasing these values, and we can always increase some other base variables, because base variables are equal to 0 in the objective function. So we can increase the values for the base variables as much as we want because they are positive. So they are satisfying the boundary constraints and increase in such a way that we compensate for this reduction by increasing this variable. So in such a way we can increase it even more, right? This variable, if we increase it even more, we will decrease these variables here. So we need to increase other base variables to satisfy the equality constraint, and the increase of this variable affects obviously the objective function, but it will the increase of the base variables will not affect the objective function because here we have 0. So this is the reasoning. Sorry, I got a little bit confused how this works. So the steps of the simplex method are as follows. We can select any column which has a positive reduced cost, for which we have a positive coefficient. So in this case, we can only select variable S1 and S2, because here we have a positive reduced cost and we have positive coefficient. And if we have more positive coefficients in the in the column we are selecting such a row for which we have the lowest simplex condition. So the division of the right hand side by the coefficient is the lowest. We are selecting such a row, and after that we are introducing such variable into the base, and we are sure that we are improving the solution, and we are doing this as long as all the reduced costs are as long as at least one reduced cost is positive and we have a positive coefficient. And we are finishing in a case either if we have all coefficients negative and positive reduced cost, so it means that we have infinite solutions, so it is unbounded and we can improve the solution as much as we want, or we finish in a case where all the reduced costs are negative. So in such a case, we know that we found an optimal solution because we cannot introduce any variable into the base in such a way that will improve the objective function. So to give you an example how this works, let us write this in the form of a simplex table. So our base is x3 and x1, because here we have unit vectors. And we are selecting certain free variable. Let us select S1 variable and let us introduce it into the base. So we are selecting a row for which we have a positive coefficient. So this is this row. And we are making a pivot on this row. So we are introducing S1 instead of X3 to the base. So here we have a coefficients for X3. So this is equal to 1 divided by 2. Here we have minus 1 divided by 2. 0 divided by 2 is 0. 1 divided by 2 is 1.5. In this column, we divided by minus value in this element. So, for example, here we have 5 divided by minus 2. Here we have minus 1 divided by minus 2, so it's equal to half. And in other elements, for example, this element is equal to minus 1 minus 1 multiplied by 1 divided by 2, so it's equal to minus 1 plus half, so it's equal to minus half, and so on. So we are calculating the values of the coefficients in all of the elements. We are calculating the right-hand side of the equations, and our objective function improved because our right-hand side element decreased. So we are selecting another element. Our objective function is equal to this value because all non-basic variables, all free variables are equal to 0. Values for, in this case, value for S1 variable is equal to 1, value for X1 variable is equal to 4. So they are equal to 0 in our objective function. So our objective function is equal to minus B0, so it's equal to 12. So we increase the value of the objective function from 7 to 12. We are selecting another column with positive reduced cost. So this is this column. We have only one positive element, so we are selecting this element to introduce this variable instead of S1 variable. So again, we are computing the coefficients for all the elements, and we change S2 with S1. So we introduce S2 to the base instead of S1 variable. And here we have all the negative reduced costs, so we cannot improve the solution anymore. And if we look at the values here, we can see that our base is equal to x1 and s2. This is our base. x1 is equal to 5, s2 is equal to 2, and this is our objective function. So in our objective function, only x1 is included, our original objective function, because in this modified objective function, all these variables are equal to 0, and this is our right-hand side of the equations. But if we write the objective function from the original problem before introducing variables into the base, it's written in such a form. So if x1 is equal to 5, the value of the objective function is equal to 15. So this is the same as the value which we obtained here. And let us solve another example. First, solving it graphically. So we are maximizing x1 plus x2, and we have 6 constraints, which look like this. So this is our feasible set. This is our objective function for certain value. So this is the level line for the objective function, and if we move it up, we will improve the value of the objective function. So the solution to this problem is obviously located in this vertex. So first, what we need to do is to reduce this example to the canonical form. So we are introducing 5 additional variables to convert inequality constraints to equality constraints. All the variables should be greater or equal than 0, so also x3 to x7. They all need to be greater or equal than 0. Next, we write these variables in the table form, and we are using the Gaussian elimination to find the first feasible point. So we are making a pivot on the selected columns. So for example, we can select those variables as base variables. We need to check the determinant for the matrix if it's different than 0, so we know that it is non-singular matrix. And then after making a pivot, we obtain the first solution. We check if it's a feasible solution. So a solution for which the 3 variables x6 and x7 are equal to 0, and these all variables have positive right-hand side of the equation, so we know that this is a feasible solution. Then we will write this using the simplex table. So all the base variables are written down here, so it's the same as we would write x1 here, right, and here is 1, and zeros below x2, 0, 1, and zeros, and so on, right? So we have such a unity matrix. Then we are selecting a variable which has a positive reduced cost, and we are selecting a row with positive value. We have such 2 rows, so we need to calculate the simplex condition. So value for simplex condition for x4 row is equal to 16 divided by 1 divided by 4, so it's equal to 64. Here we have 28 divided by 7 divided by 4, so it's equal to 16. So we are selecting a row which has a lower value. So this is this element, and we are introducing this element to the base. So we are changing x7 with x5 by making a pivot on this element. So we are computing all the coefficients for all the values, and we again check if there is a reduced cost with positive value. And here we have the reduced cost with positive values. So we are looking for a row with positive coefficient. We have 2 such rows, so we need to compute the simplex condition. So here we have 10 divided by 2 divided by 7, so it's equal to 35. Here we have 12 divided by 12 by 7, so it's equal to 7. So this is the lower value, so we are selecting this row. So we are introducing variable x6 into the base instead of x4. So we need to make a pivot on this element. And after making a pivot and computing the coefficients, we have all the reduced cost negative. So we know that we found an optimal solution. So we can write the values for all the variables such that the free variables are equal to 0. So this is our first basic solution. So here we have the values for variables x1 to x5. We can write them down from the right-hand side of the equations. Values for the free variables are equal to 0. That's why here we have zeros. This is our second solution. So this is our base. So we can calculate the values from the base from this table. So we have values for x1, x2, x3, x4, and x7. Values for free variables are equal to 0, and the same goes for our third base vector. And then we know that the optimal solution is in our third base. So value for x1 is equal to 8, value for x2 is equal to 10. So it's at point 8, 10, and the value of the objective function is 18. So by looking at this table, we can see how the simplex performs. So our first point is equal to 6, 1. So we started in this point. The value of the objective function is 7. Then we move to this point, so it's equal to 10, 5. So it's here. We move to this point. The value of the objective function increased from 7 to 15. And then we move to this point, 8, 10, which is here. And the value of the objective function is equal to 18. And from this point, all the reduced costs were negative, so we cannot move to any vertex to increase the objective function. So if we had a minimization problem, it's required to multiply this value by -1, so we know that the value of the minimization problem is equal to -18. So this is how the simplex works in two-dimensional case. Obviously, in more dimensional cases, it's not possible to visualize the way how this method works, but the idea is that we reduce the number of visited vertices. So in the naive algorithm, we would need to check all the vertices. This is a very simple case, so we have only 5 vertices. However, the simplex required to check 3 of them. So imagine a case where we have many dimensions, a huge number of vertices. So this way of improving the solution by checking only some of them can speed up calculations a lot. And we are assured that we are assured that we will find an optimal value, or we will know that, for example, the problem is infeasible or unbounded, so there are so the solution is infinite. So okay, let me finish this lecture on this slide. If you have any questions, feel free to ask. If not, thank you for your attention and attendance.
Well, I can have a question regarding the project, not the lecture.
Sure.
But I can wait so the others can leave, because they don't need to be here if they don't want to.
Okay, so if any of you also is interested in the question, feel free to stay. If not, feel free to leave. So please go ahead.
Yes, everyone are interested in my question. Well, I have a question regarding the first stage of the project.
Okay.
Because I didn't upload it yet, because I'm still considering how to properly add the constraints to the functions. Because really,
okay.
I'm not. Oh.
Okay, so let me answer at this moment, and then you can extend your questions. So
Mhm.
you are at this moment, you are not introducing the constraints to the function. There will be a method with penalty function, which I will show you. And this is the approach how you introduce the constraints. But for now, you should just write the focus on the only the objective function, how to visualize it. Then you should draw the constraints. After that, in the project, it is required to implement two methods, a gradient-based and non-gradient-based. So I would suggest as a first step to implement those methods and not consider the constraints at all. And after that, I will show you a method how to include the constraints into the objective function. So you are included them as using by the penalty function. So if a considered point of your algorithm will violate some of the constraints, the objective function will increase significantly if it's a minimization problem. But such introduction constraints to the objective function will not require to modify the implemented algorithm. So I would suggest for the first stage just to visualize the function or eventually add the constraints to the visualization where they are located. And then on the second stage, it's required to implement non-gradient based algorithm. So just to implement it for the case without constraints, because it will be probably easier, and then introduce those constraints if you will have a time to focus on this modification of this problem. But if you have some other idea, of course, you are free to select any approach which is comfortable for you.
Okay, so basically for the, sorry.
Yes, please go ahead.
So basically for the first stage, we didn't have to upload any constraints unless we want to show them in X and Y. And yes. Basically, oh, okay, my bad.
I mean, you can draw them using different color, for example. So you can in this level graph where you have the levels for the three-dimensional function. So where you are making different colors for the values of the objective function, you can add those constraints as lines with different color. But I mean, you can also draw them on another chart. So just draw how the constraints look like. Okay.
Okay. Thank you.
Okay, I hope it's clear. So do you have any other questions regarding the project? There is a place on the portal where you should upload a PDF and a source code, or you can include because it's a little amount of source code, so you can include this source code in PDF as well.
I have another question that's more specific for me, but I can't see the subject in the portal.
You cannot see anything on the portal. You are the person who sent me an email, right?
Yes. Okay,
because it was just before the lecture, I will add you to the e-portal, but because probably you are not, because you are enrolled. Okay, so because you send me an email, so I have your ID number, so I will add you after the lecture, okay, to the e-portal.
Okay, so, perfect, thank you.
So after that, please read the, on the e-portal, you will have all the materials regarding the project and slides for the lecture. So please familiarize yourself with the requirements for the project. And if you will have any questions regarding that, so mail me or use MS Teams to contact with me. And if there will be any need to clarify some issues with the project, okay?
I want to ask a question, but maybe like show you my constraints that I did, and just to ask you if it's correct.
Yes, of course. I mean, because I have another lecture in 15 minutes, so after this meeting, you can just show me by sharing the screen on MS Teams, or you can mail them to me and I will respond to you. So, okay.
Okay, then I will call you on Teams.
Okay, sure.
Thank you.
You're welcome. Okay, so so see you next week, I suppose.
Okay, thank you, sir.
Thank you. Have a good week.
Have a good day.
Yes, you too.